This video is on AP Physics C 2024 actual exam, set 1, question number 2. So let's talk about this. The student drops a cylinder of mass m from rest. The air exerts a drag force of magnitude Fdrag on the cylinder as shown in figure 1. The student models the magnitude of the drag force as bv square, where v is the speed of the cylinder and b is a positive constant with appropriate units. Derive but do not solve. Okay. Uh, a differential equation that could be used to determine the speed v of the cylinder as a function of time. Express your answer in terms of the given quantities and physical constants as appropriate. Let's draw an FBD for this one. So I know that there's a drag, but obviously there is a force, the popular one, the gravity, which is continuously pulling this thing down. Eventually it is going down. So what is F net, guys? F net, which is going down, is obviously the downward force minus the gravity force, which is upwards. What do we need to do? We need to find a differential equation to find the speed and time. So V and T, that's the relationship which we need. So I think that's pretty straightforward, right? Because I know that force is ma, F net is ma. So ma is going to be mg minus bv square, where v is a constant, of course. So we really need to do at this point is to replace the acceleration with dv over dt. So dv over dt is equal to mg minus bv square. And I think this is the differential equation, right? I mean, if you want, we can isolate dv over dt by dividing both sides with m. So it will be g minus bv square over m. That's going to be the differential equation from which we can clearly find the value of, or the relationship rather, between the velocity and the time, because there's no other variable over here. So this is what we solve this question. As. Okay, all right. So we have this. Next question is, the student correctly sketches the velocity of the cylinder as a function of time. Draw a vertical line on the sketch in the figure T2 to indicate the earliest time at which the drag force is equal to the weight, and label this time as T1 equal to the on the time axis. Okay. Um, when the net force is 0, then the velocity will be maximum, right? Because they are saying that when drag force is equal to the magnitude, it obviously doesn't stop there. It won't make sense because the net force is 0. They are saying that these two should be equal, right? And if these two are equal, then obviously the net force is 0, right? I hope you understand what I'm trying to say. I'm saying that F net is equal to mg minus bv square. They are saying that mg should be equal to bv square, which means that mg minus bv square will just be 0. So F net is 0. It means that ma is 0. It means that a is 0. So either the body is at rest, which is obviously not possible, or the velocity is maximum, because the acceleration is 0 only in two cases: when the velocity becomes constant, sorry, not maximum, constant, or the body is at rest. Rest is not possible, so velocity should be constant at this point. And clearly the velocity is constant the first time when this happens is obviously when it flattens out. So I would say this time, exactly this is the time when the gravity force and the other force, the drag force, is going to be equal to each other. So this is how we indicate this. Let's see what is the next question. Justify the location of T1, explicitly reference appropriate features of the sketch. I think we have already justified, because I just said that the acceleration is 0. Acceleration is 0 means the velocity is constant. You can also say that acceleration is 0 means the slope of v versus t should be 0, because that's what it means, right? The slope of dv over dt is the slope, and the slope is 0, and this is a horizontal line. So at all these points, in this entire line segment, in fact, the drag force and the weight are equal, but they are saying the earliest time. So obviously the earliest time is when this gets started. So in a way we have already answered two, and then actually we answered the first one. So yeah, that's we are through with this. Right, let's talk about the next question. Rather than dropping the cylinder from rest, the student throws the cylinder upward with a non-zero velocity, initial velocity. Okay, we don't know what the non-zero speed. We don't know what the speed is. The cylinder is in the same orientation as when it was previously dropped. The student allows the cylinder to fall towards the ground. Indicate whether the magnitude of the cylinder's maximum downward speed after being thrown upward would be greater than, less than, or equal to the maximum speed. I think it's going to be same because we might be overthinking if we go deep into this, that what was the speed from which it was thrown, going up, down, work done, not required, because all we have to do, we know that the initial situation was the maximum speed is when BV square is mg, right? I mean, what's going to change? Because in this case as well, you are going to do the same thing. It doesn't matter whether the cylinder is first thrown up, then it comes down. Still, I'm going to do the same thing, that whatever BV square, B is not going to change, is equal to mg. M is not changing. So initially also the velocity was root of mg over B. Now also the velocity is root of mg over B. So it's going to be equal, right? Nothing is going to change because these are the only two forces which are acting on it. No other forces are acting. B is same. Nothing is changing. That's how we can justify it. So, in fact, we have mathematically already justified. So that's how it works. All right. The next one which we have is the student conducts an experiment to better understand the relationship between the maximum speed and the mass. Okay. All right. Interesting. The student collects the data to determine the maximum speed for the cylinders drawn from rest, each with the same physical size and shape, but with a different mass m. The student then graphs the v square max as a function of the mass. So this is v square, this is mass. Draw the line of best fit. So this is pretty much drawing the line of best fit. Nothing too fancy here. We just try to draw the best line which we can. So I think uh, um, let me take, I think this will work. Yeah, I mean, okay, that point is being missed. So maybe this is, yeah, this looks okay. Yeah, I think this looks okay. Okay, all right. Use the line of best fit to calculate an experimental value for B. So that's for that we need to go back to our equation which was relating V and mass. There you go. BV square is equal to mg. So let's come back here and write that since BV square is equal to mg, so V square is equal to g or maybe mg over B. So V square, which is y square, is equal to m, which is g over B, times x, which is m, right? Because that's what we are finding. That we are finding V square versus V square versus m. So this is what we have. So we know that the slope is this one, right? Um, so use the line of the best fit to find the experimental value of it. So when we write this over here, we just need to take two nice and cozy points so that we can find the slope. Let's see. I think this is one of the point, right? This is one of the point. This y coordinate is 8 and the x, yeah, it's 0.025. So 0.425, 0.45. That's the middle. Oh, that's the middle, right? Okay, so the x coordinate is 0.45 and the y coordinate is 8. That's the first cozy point which we have. The other point is this one. Let's avoid taking that data because that's a data set point as well. Let's take this one. So this one is again 0.15 and this one is in the middle, that's 3. So that's 3, sorry, that's 0.15 comma 3. So what is the slope? y2 minus y1, which is 5, over x2 minus x1, which is 0.3. This can also be written as 50 over 3. So I know that 50 over 3 is going to be the slope, which is g over b. G can be taken as 10, or let's call it as 9.8. So I'm going to grab my calculator now. So where is that? yeah, 9.8 over the value of b. So the value of b from here comes out as 9.8 times 3 over 50, 0 0.588, 0 0.588. What would be the unit of this? The unit is going to be, this is meter per second square. I don't think so they need the unit, do they? I think that should be okay. We don't need to mention the units. So that's 0 0.588 approximately. That's what I'm getting from here. All right, let's move ahead. A student claims that the magnitude of the maximum speed of the cylinder dropped from rest depends on the length of the cylinder. A student designs an experiment to collect data that can be used to provide evidence to support the claim. The student drops the cylinder with the orientation shown in figure 3. The student has access to but does not have to use all of the following equipment. So cylinder set 1, cylinders of the same known cross-section of different known masses, of the same known masses but different known lengths, a motion detector that can measure the velocity as a function of time. Indicate the two quantities that when graphed could be used to determine whether the length of the cylinder affects the maximum speed. Obviously, it makes sense that why will we change the mass, right? Why will we change the mass? Because we are not even experimenting that. So all we have to do is see that whether the independent variable, which is in our hands, which is length, because that's the independent variable. So independent variable should come in the horizontal axis, and the dependent variable will be the one which we are trying to find, which is the velocity, which is changing. So briefly examine, now they are saying that briefly examine that how the quantities graphed could be used to determine the relationship between the cylinder length and the maximum speed. What are they trying to find, by the way? They are trying to prove that magnitude of the maximum speed dropped from rest depends on the length of the cylinder, right? Depends on the length of the cylinder. They are not saying it's increases or decreases. So what can we, what do we know? We know that if the graph of velocity versus length comes out to be almost a horizontal line, then it is not dependent. But how will it be dependent? How will the relationship change? If it is anything not which is not a horizontal line, maybe it's an increasing curve or a decreasing curve, right? Then there will be a relationship between them. There will be a change. So we can say that if horizontal or almost horizontal, if horizontal implies no change with length. However, if increasing or decreasing, this would mean that yes, there is a change of velocity with the change of the length of the cylinder. This is what we can say. Right, so I hope this makes sense. This was all about question 2. In the next video, we'll talk about another question. Till then, take care. Bye.